Welcome back. This is the final video of the course. I'll offer a very short and very rapid summary of what we covered in the course. First, of course, we looked at the introduction and looked at what inverse problems are. In that, we tried to figure out the cause from effect, and that makes inverse problems a really general topic for all of science and engineering. Specifically within heat transfer, we saw a few examples. We just looked at a couple of examples, illustrative examples within the class. In case this were a live class, we would have done a whole lot more, but in video recordings, only so much could be done. But we, keeping with the name of the course, we looked at several methods. So the methods that we looked at were first, of course, linear models, which could be used for inverse. And within that, we saw linear regression, polynomial regression, weighted linear regression, etc. Then we looked at nonlinear regression, specifically Gauss-Newton algorithm. Then we looked at variants of Gauss-Newton algorithm, which were Levenberg-Marquardt and Tikhonov, which were used as regularization techniques for these. So these two were regularization techniques. Then we switched our attention. This was our first set of techniques. The second set of techniques were probabilistic techniques, where instead of interpreting the problem as one of simply finding a function, we interpret the problem as trying to find out a probability density function. So after introduction to probability and all the other terms, we looked at the Bayesian approach, specifically using the Metropolis-Hastings Markov chain Monte Carlo. The Metropolis-Hastings is basically a sampling technique where if you can't do, or if you don't wish to do offline Bayesian because it is really expensive, you start sampling so that every sample text tells you where next to look. So Markov chain Monte Carlo is simply a probabilistic technique or a technique to reconstruct the probability density function. And we saw how once you know the probability density function, you can actually find out a whole lot more, not just the parameter, but also the uncertainty in the parameter. Okay, whereas whether it is algebraic techniques or machine learning techniques, we look only at the final answer rather than the uncertainty involved in our determination. Finally, we looked at machine learning. The last 4 to 5 weeks were primarily on machine learning, where we looked at an introduction to neural networks. We looked at physics-informed neural networks, and we also saw how surrogate models could be used. Now, what is it that within this course we did not cover? As I had said earlier, this is basically an undergraduate course, and that too a really introductory one. What we did not cover is a vast set of topics that make it for a graduate course. So we did not cover, even though I mentioned briefly about how sensitivity matrix could be used for using design of experiments, designing where to put thermocouples, how exactly to find out uncertainty. All these topics were not covered within this course. Secondly, we only looked at parameter estimation. That is, we just assume that we know only, we want to find out thermal conductivity or some such parameter, whereas usually you would, not usually, but in some cases, you have an entire function to be estimated. For example, let's say the thermal conductivity varies across an entire body. So K is now a function of X. In such a case, you would need a function estimation approach. There are other cases, such as in turbulence, where you need a function estimation approach. Of course, finding out the entire Q as a function of time also is a function approach, function estimation approach. Adjoint techniques, I had briefly referred to this. These come in two different ways, even though the meaning actually comes in the same way. Adjoint techniques can be direct techniques to write what is known as an adjoint equation to the governing differential equation, which lets you find out things like derivatives such as sensitivity coefficients directly. Turns out it's also very useful whenever you have function estimation problems. One other thing that I did not discuss, which actually I was planning, these other techniques that I told you, the other 4 topics that I told you, I was not planning on covering anyway, but Some practical techniques to solve inverse problems with CFD would have been an important topic. Unfortunately, time did not permit me to discuss this. The idea is, in cases where we don't know analytical solutions, even though I showed neural networks, traditionally people tend to use normal CFD computations, out of which you build surrogate models. So to walk you through a full case study would have been nice, but unfortunately we did not get time to cover that. Nonetheless, I hope you found this course covering a wide variety of techniques useful, and I hope you continue your journey in inverse methods, because it's a vast topic. And as I said in the beginning, it covers, in fact, many topics can be thought of as special cases of inverse methods. So I hope you continue your journey here, and I was a little bit useful in encouraging you to learn a little bit more about the subject. Thank you very much.